Just want to say it's a great honour to be here. Thank you very much for the invitation to come to Japan and present to the SIP. And also congratulations to the Research Institute for 100 years. So I'm from the National Institute of Water and Atmospheric Research in New Zealand. We've been around for 33 years and today's the last day of the Institute. So tomorrow we become the Earth Science Institute and we join with GNS Science. So we're an amalgamation of different Earth Sciences Institutes and hopefully that makes our work a lot more efficient and effective in the long term. So while we're in a earthquake engineering building today, my presentation is going to be focused on flooding hazards in New Zealand and a program of work that we've undertaken in the last 5 years to better understand our flood hazard, but also produce some of the tools and data sets that people like Sarah Jane and local and central government need to make better informed flood risk management decisions. So my presentation today, I'll provide some context of New Zealand's flooding problems. Then I'll go into the program of work to develop the models and tools that enable us to map and understand flood risk. And then also cover a couple of applications which I think are relevant to the SIP project that have spun out of the work that's been done on developing flood and hazard and risk models in New Zealand. Okay, so just to set the scene of New Zealand's flood problems, so I borrowed this slide from a colleague of mine who went back over the last 5 years and just looked at some of the flood events in New Zealand's recent past. So flood events are causing on average around anywhere sort of between $100 and $200 million per year over the last 5 years, and it's been a slow increase in terms of year-on-year increases in flood damage. But just going back the last 5 years, this is just a selection of some of the flood events. So in 2019, there's the Rangitata River in the South Island, which breached its banks and did a lot of infrastructure damage. The following year, up in Northland, more riverine flooding, affecting communities, quite small communities that have been repeatedly flooded by events over several years. And then move into pluvial flooding in Napier, so in the North Island, a low-lying settlement on the coast, which has a pluvial flooding issue, but potentially also a coastal flooding issue. So pluvial being flooding directly from rainfall. More pluvial flooding in New Plymouth, also in the North Island. Another big event in the South Island. This was the Ashburton River, which is just south of Christchurch, caused a lot of damage to agricultural land. Westport, also on the South Island, is a town which sits on the Buller River, which is quite a large river system on the west coast of the South Island. Westport has 100 years of just repeated flooding through the township and was flooded badly in 2021. This is Cumia in Auckland, which has another settlement which has been repeatedly flooded in the past several years, and there's actually discussions at local government about moving the entire township. Whether that happens is probably unlikely given New Zealand's history of decisions in building in floodplains. This is Tairāwhiti, so Gisborne. This is pluvial flooding from rainfall. Back to Westport again. So Westport was flooded the following year by the Buller River. Auckland has a frequent pluvial flooding issue. So this is where many years of underinvestment or maybe the wrong investment in stormwater infrastructure means that it doesn't take too much water to overwhelm the system and cause local flooding. Sarah Jane had a slide of Nelson. So Nelson's also been repeatedly affected in the last over a 10-year period by atmospheric river type flooding events, which has dropped a large amount of rain into small catchments and caused this type of damage to infrastructure. And then in 2023 we had New Zealand's two biggest in terms of economic cost flood events in its history. starting with the Auckland anniversary weekend floods at the end of January in 2003, which caused multiple billions of dollars of damage to buildings and significant disruption across the city. And this is the Auckland International Airport, which was under about half a metre of water through the main terminal building, followed 2 weeks later by Cyclone Gabrielle, which Sarah Jane has some stats in terms of the level of damage that event caused. And then following years, more and more flood events and the repeated locations as well. And then as we were flying out of New Zealand on Friday, there was also a significant flood event involving at the northern part of the South Island. So the Nelson and Melville regions were underwater as we were leaving the country. So the first problem is we have lots of floods around the country. They're not focused in any one location. It's just everywhere floods, and we have development in all of these locations. So there's always something that gets affected. The other problem is what climate change is going to do to the present state of the flooding hazard. So the early indications from climate modelling suggest that the main change in flood regime that we're going to see is a change to the shorter duration floodings. So these are the sort of short duration in terms of time, but really intense sort of rainfall events. So the situation like Auckland, so short duration flooding, high intensity rainfall, will this be the norm that we see in the future? And the climate models are indicating that the current volume of rainfall from these events could increase by around 14% for a 100-year flood hazard. So that's a significant amount of water that could occur with these shorter duration events, and our infrastructure, particularly in our towns and cities, is not equipped to handle this type of flooding situation. So the third problem that we have with flooding is decentralized management of flood risk. So the main driver of this, which Sarah Jane mentioned, is putting the sort of local responsibility onto local government and communities to manage their risks. But what this creates in practice is a bit of an inequity in how flooding is investigated, and builds an understanding of local flood risk. So a well-resourced region like Auckland, which has a high population, is relatively well served with flooding maps, whereas on the flooding maps and also an understanding of the local risks, whereas on the west coast of the South Island, with a low population and low resource base to do flood investigations, has in comparison, little information about its flood hazard and risk, despite quite a prominent flood hazard in that location. And actually, the way that the resource management is set up is that a lot of the flood investigations happen as the result of a resource management activity that needs to be addressed. So even in a location like Auckland, which has a lot of flood hazard information, it's often inconsistent between locations because a new consultant will do the flood modelling on behalf of the council for a location to serve a purpose. The next activity, another consultant will do the flood modelling, use a different technique, look at different scenarios to serve a different resource management purpose. So and this is not specific to Auckland, this is across the entire country. So what we end up with is a lot of inconsistency in our flood hazard and risk knowledge, which has also led to a limited understanding as to what New Zealand's overall flood risk is. So to address this problem, we're just coming to the end of a 5-year program of work funded by the Ministry of Business, Innovation and Enterprise. And the project rationale was to create consistent hazard and risk information across the entire country, and also make this information accessible at all societal levels, so that there's a consistent flood hazard and risk data set, which is available not just to central government and local government, but also available to the New Zealand public to identify what their exposure and risk is to flood hazards. So a key objective of the project was to develop a workflow which is consistent and repeatable to generate nationwide flood hazard and risk models and maps. And that another objective of this project was to create a forum between scientists and stakeholders to ensure that the uptake of hazard and risk information was being done for everyday flood hazard risk decision making. So my presentation today, I'm going to focus on the first objective, which is the development of the workflow. So this is what our overall workflow for a nationwide flood hazard and risk model looks like, and these are the key components of the workflow. So over the next few slides, I'm going to step through each component and explain which each one does, and then also how it operates in practice. So firstly, we start off by identifying a simulation domain for creating a flood map. So to model the entire country of New Zealand in one domain is impractical computationally. So the simulation domains identify specific geographical areas in which to focus attention of the model. What we do here is that we identify the domains based on the river network, the topography and soil classes, as well as what's at risk within that area. So like Japan, a lot of New Zealand is mountainous, and there's very little in terms of asset and population in some of these mountainous locations. So rather than undertake a full numerical model of those locations which are of less interest in terms of the risk from flooding, we use the domain tool to identify which part of the simulation domain we run a hydrological model, which just simulates the flow within rivers, and then which part of the simulation domain we undertake inundation mapping. So these are generally the areas that are exposed to, or have exposure to impact from flood hazards. So once the simulation domain's been identified, develop this tool called GeoFabrics. So GeoFabrics is an open source Python package, which is set up to create a hydraulically conditioned digital elevation model and surface roughness map for the simulation domain. So the elevation model is developed utilizing LiDAR, which the New Zealand government has made available through a site called Open Topography. It also uses, and to create the hydraulically conditioned DEM, also uses the OpenStreetMap River Lines network to identify where channels are located, as well as other flood structures like culverts, bridges, drains. So what the GeoFabrics tool does is that it creates an elevation model of the land that also includes the river channels. So including the bathymetry of the river channels and also the bathymetry of estuarine and nearshore environments is all integrated into the same elevation model, which means that you're covering the shape of the river channel, which has a large bearing in terms of how much water is held within the channel before it breaches the banks. So the next step is to create a design storm. So the design storm event is the rainfall, a design storm is a rainfall surface, which is both spatial and temporal. So most flood inundation models will drop a uniform rainfall rate. So X number of mils over, say, 24 hours goes into the simulation domain. That's sort of the traditional method of including rainfall in a flood inundation model, whereas the design storm represented by the line graph here demonstrates that the way that rain falls into a simulation domain over the course of a storm is not, it evolves over the duration of the storm event. So the design storms are to represent how the water falls into the simulation domain as an event's evolved. A hydrological model is the component which simulates the flows in the river. So once the design storm simulates the rainfall, this feeds into the hydrological model, which simulates the flows in the river channels. As well as having the hydrology simulated for the river channel, the rainfall, there's also the tides as well. So as part of this, a national tidal model is coupled with the rainfall and flow models, so that the tide is being simulated at the same time as over which the storm is occurring. So traditionally, these models may pick a certain tide level and model at that level, whereas this model simulates the storm event and the tide happening in concert. So with the hydrology resolved, we now move into the hydrodynamic model. So this is the numerical model which generates an inundation map. And we developed a numerical modeling application called BG Flood, which is a model that's set up for modeling shallow water hydrodynamics on a graphical processing unit. Using an adaptive mesh. So the principle around the adaptive mesh is that that greater resolution is applied where it's of most need, so that locations that say we're not so interested in accurately resolving the flood hazard, we can treat with a coarser grid, whereas locations where we do want a high resolution output, we can refine the grid. So the purpose of BG Flood is also to be a somewhat flood agnostic type model. So we do actually apply this this model for coastal flooding and also tsunami as well. So we can simulate different inundation hazards using the same software, but changing the context. I think there you go. Got to press play. So yeah, so the graphic there shows the refinement of the flood, of the mesh down to finer resolutions where there's most interested in an accurate result. And then finally, once an inundation map of the flood hazard intensities has been produced, we can then feed the flood inundation map into a risk modelling application that we've developed in New Zealand called RiskScape. So RiskScape's an open source multi-hazard risk modelling engine. So kind of like BG Flood, we use RiskScape not just for modelling flood risk, but also for seismic risk, tsunami, volcanic hazard, anything. So RiskScape has a concept of a model pipeline. The model pipelines are user defined, so that they're not specific to any specific standard. So unlike a software like OpenQuake, which has prescribed standards in which input data to the model must adhere to in order to utilize the calculation workflows, these workflows are user defined in RiskScape, which means that we can use it for flood hazard in this context. It generates the traditional catastrophe risk metrics like expected annualized damage, but it can also be configured to run flood scenarios as well. So what if a levee breached at this location? What might the dollar cost in terms of building damage be to the area affected. So the operation of this workflow is not trivial. So what we've utilized in order to manage each component in sequence, and manage the sequence at which they are implemented in the workflow, is a workflow engine called Silk, which was developed at NIED for scheduling the various tasks that are required to run weather models. So because it's a somewhat agnostic scheduling software, it means that we can manage the tasks required in each component of the workflow in sequence, so that the dependencies between tasks are met before the next sequence is triggered. So at the moment, the workflow is set up on a high-performance computer, and at the moment it models the hydrodynamic part of the model, but we will extend this in the future to include the risk model as well. So this will mean that once the workflow is triggered for a simulation domain, it'll work through a process of simulating the flood inundation hazard and the hazard intensities, but then it can also simulate what the impacts from the flooding scenario are as well. So Silk is also an open source software package which is available on the link below, and quite well used around the world for weather forecasting. So that was an overview of the workflow that we've used to create nationwide flood maps for New Zealand. And then several applications have spun out of the development of this workflow, which I'll cover in the next few slides. So the first application was applying the flood hazard maps that have been generated nationwide to estimate New Zealand's national building risk to flooding hazards. So what we've done with the workflow is that we've generated nationwide flood hazard maps for different recurrence interval events, and then developed an object-specific exposure inventory of New Zealand's buildings. And then this has been made possible from government investment in mapping spatial features. So Land Information New Zealand has, over the past 6 years or so, continually mapped New Zealand's building outlines and then made this information available on a public GIS portal. So while there's limited information about what the buildings are, having the location of the buildings is kind of the first step for us to be able to simulate the characteristics of the buildings, and those characteristics which make them more or less vulnerable to damage from flooding. A major knowledge gap that we've had to address has been the vulnerability of different building typologies to flood damage in New Zealand. So we've undertaken a program of post-event impact surveys, which I'll cover in the next slide, to build up an empirical damage database to develop machine learning models for physical damage prediction. And then our risk model pipeline implemented in Riskscape enables us to integrate these data sets and then calculate the expected annual damages from flooding for buildings across New Zealand. So over a 10-year period, we've been collecting on-site physical damage information about buildings, which has built up an empirical damage database, which now roughly corresponds to about 2,300 building damage samples, and provides, for some buildings in particular, like our residential building stock, a fairly good overview of the types of damages that we may expect to see from flooding events in New Zealand. We've then trialed different machine learning algorithms to learn based on the damage observed, as well as the exposure characteristics and the hazard intensities that have occurred on site, what a relative damage outcome may be. And then we've I guess tried to build an understanding in terms of like, how best to apply the machine learning algorithms in different flood risk contexts. So we've done some investigation around how an algorithm that's trained for one event may predict flood damage for another, and where the shortcomings are. So for instance, we see that buildings that are being flooded from a levee breach, the model may over-predict the damage if it were applied in a flood situation which was, say, caused by rainfall flooding alone. So a more sort of low energy type situation. So in terms of the outcomes from this national risk assessment, so what we've achieved is essentially a national building catastrophe model for flooding in New Zealand. And we're able to generate metrics such as expected annual damages. So these are the first estimates, and I haven't presented these yet, so this is the first time that I've been able to present this work. And we estimate that New Zealand's annual expected damages from flooding is roughly $196 million, which is sort of in line with what the insurance sector is reporting as well. So I guess that's a useful validation for us. We can also look at the expected damages for an individual flood event. So for a 1% AEP or 1 in 100 year type flooding event, we could expect to see around $2.7 billion in impacts across New Zealand. And because we have modelled this information at a building level, we can also see where across the country the greatest risk lies. So we can see that several regions, such as Canterbury and Waikato, equate to over a third of the risk. And then we can also see that residential buildings and buildings used for primary production account for the major proportion of the risk as well. In our object-specific inventory, we have a characteristic which is the year the building was first built, and we can see that while the relative rate of building development has reduced slightly over time, the buildings are actually getting bigger and more expensive. So we're not actually reducing the risk by continuing to build in floodplains. So another application was using the workflow to create flood hazard maps for ex-tropical cyclone Gabrielle. So the idea behind this application was funded as part of the extreme weather response. So the government provided some funding to do research to help inform the response and recovery from Cyclone Gabrielle. And one of the projects, well, two projects actually, that we undertook, one was using the workflow to simulate the hazard, the flooding hazard that is, and then also develop a couple of tools that would support government agencies with trying to better understand what happened in terms of flood impacts from the event, and use these tools to stress test different, say, development scenarios during the recovery process. So in terms of the flood map generation, what we've done is we had some of the components of the workflow in place, so the geofabrics and the hydrological model. So we could adapt the workflow by creating the simulation domains, generating the design storm for the ex-tropical cyclone, and then plug those data sets into the workflow. We could also refine our areas of interest, so using a high resolution mesh where the damage occurred, and lower resolution where there was less damage. I'll just see if the so I've got a simulation on the right. If I click on that, looks like there's a flood happening. Okay, great. So what we've found with the hydrodynamic model is that the the better we could represent the design rainfall for the event, the closer match we got to representing the extent of the flooding hazard, but also the flood hazard intensities in terms of the water depth above ground. So, so this was a really promising exercise for using the national workflow, but for a specific event, and generate a high resolution data set across multiple regions that, that our practitioners could use to help inform decision making on sort of the flood hazard response. So the other component of work was developing a web-based platform that would not just be a static data display, but would also enable practitioners to engage with the flood impact and risk models themselves, and run these over the web. So as part of this work, we developed what's called a microsite. So it's a basic website that has specific functionality required for a task. And in this case, we developed a microsite which provided a tool to model impacts from flooding for different economic sectors and population as well. So what the tool enabled practitioners to do was, without having to be technically across how to run a risk model, was to select which, say, hazard scenario they wanted to model, which exposure, and then what impacts, and then simulate those online, and then also derive spatial maps, but also tabular data, which would provide the numbers behind the impacts as well. And then also there was another microsite developed with a multi-hazard risk model sitting in behind it. So this included not just flooding, but also earthquake, tsunami, coastal flooding, because the Hawke's Bay is a very hazardous location. These locations where recovery was being carried out could also be affected by these other hazards in the future. So in order to provide some tools to look at what those future hazard risks may look like, that came into a specific site to do that type of modelling. And then there were also some features like risk matrices, graphing tools, which enabled the user to look at, say, marrying up the risk levels with what might be defined in a local resource management plan. So the final application I'll cover today is a application on forecasting flood impacts at Westport. So Westport was the township I mentioned earlier that had been repeatedly damaged from flooding over the past 5 years, over several events. So what this project looked to achieve was to develop a trained machine learning algorithm that could generate a representation of flooding hazards in a matter of minutes, as opposed to, say, 24 hours, which a traditional numerical model might simulate the flooding hazard over. So an AI-based algorithm works conceptually like this. So what we have with the national workflow is that we have the ability to generate a large set of simulated flood inundation hazard maps representing different river flow and different tidal conditions. So these are the characteristics of the flood hazard which are forecasted. So having a large pre-trained library of these scenarios enables us to train machine learning algorithm. So in this case, a convolutional neural network model. We can pre-train the algorithm to generate an event set of maps, but we can also use the trained algorithm in the context of a rainfall forecast to simulate what flooding may look like in a location and represent that flooding as a two-dimensional spatial map. Oops, sorry, wrong way. So when rainfall's been forecast, it's actually been forecast using an 18-member forecast ensemble. So we just don't have one forecasted rainfall, we've got 18 different simulations of what the rainfall may do. So what we're able to do with each rainfall forecast is that we can simulate the flow conditions under which each ensemble is telling us, and generate hydrographs that we can then plug into our machine learning model, along with the tidal predictions, to simulate what flooding may look like at a location over the forecasted storm event. So the simulation on the right is showing, based on the 18-member ensemble, what the probability of the location getting flooded may be based on the ensemble of forecasts on the left-hand panel. So while this is a probability of the land getting wet, sitting in behind this information is also the two-dimensional representation of the flood hazard, so the flood extent and the water depth above ground, which we can then apply in an impact model to work out what the damage to buildings may be, what the damage to roads or the loss of road service may be for a location. And we can generate those impacts at different time steps of the hydrograph. So as the flood is evolving, we can get a hourly representation of what the potential impacts at a location may be. So to help emergency managers with prioritizing which locations are of highest priority to implement a response, so that could be to evacuate the residents that could be in harm's way. This type of information provides those impacts ahead of an expected flooding event at the location. So I just wanted to finish on some potential opportunities between Japan and New Zealand. New Zealand, I guess, trying to come up to speed in its national understanding of flood hazards and risks. And I think there is potentially some mutual interest between our countries in developing national flood catastrophe models. Both our countries are working hard on developing these models, particularly in the seismic hazard space, maybe less so in terms of flooding. So I think there is an opportunity to learn across both countries in terms of how we're approaching the development of national catastrophe models, and also the tools in which we're using to create these models as well. So a lot of the time these models are somewhat location agnostic, so they can be, say, picked up in New Zealand and applied in Japan, and vice versa. So the local context obviously changes. The techniques for rapid flood hazard and impact mapping is definitely an area where I think the two countries can collaborate on. Both our countries are mountainous. We have short, steep catchments with very fast flooding times or short duration flooding events. So there's a lot of commonalities there around the need for speed in terms of generating flood impact information, and then of course disseminating that information to stakeholders in a way that's easily digestible and usable to make flood response decisions. Yeah, and then finally is the transfer of some of these hazard and risk modelling techniques to other hazards. So we see potential in New Zealand for the use of, say, the geofabrics package, which creates hydraulically conditioned DEM to be used in our tsunami inundation modelling and our coastal flood inundation modelling. So by doing that, we create an economy of scale around using a single software and methodology to serve multiple purposes for mapping national hazards across multiple hazard types. So it would be really interesting to see how that type of product or that type of method would work in Japan, and then also what's applied in Japan and whether that could be used to make products like geofabrics better. Thank you for your time.